Today we will discuss about the coupling of the electric flow and the heat, and then we will go further with the mechanical field. And when we have discussed the mechanical field, we will have the full three-field coupling from electric flow, heating being the heating sources, the joules losses to heat up, for example, semiconductors, and then to be able to compute the mechanical stresses coming up in electronic devices. So, as already told, the heating losses, or mainly called joule losses, is the product between the current density you have within your device and the electric field intensity E. And we know that we have this constitutive equation that we can express the current density by the electric conductivity via the electric field intensity E. And so we see it is proportional to the square of the electric field intensity E. And as we know, we have the relation between the electric field intensity E, which in our case is just the irrotational part, and therefore we can express E by the gradient, or to be correct, by minus the gradient of the electric scalar potential phi. So in this sense, we have here the coupling from the electric flow equation to the heat equation. And the main coupling back is that the electric conductivity, gamma, is a function of the temperature itself. You can see here in this sense just the dependency on this electric conductivity in steel over the temperature, and you can see how it decreases with increasing temperature, which is a standard within metal materials. So what we also see here is that actually this coupling makes, even if we model the heat as well as the electric flow equation as linear partial differential equation, the coupling is inherently nonlinear. Okay, so when we now look to our equations, we know the partial differential equation for the electric flow expressed by the scalar electric potential phi here is nothing else as a Laplace operator. We should not forget that we have here the electric conductivity, and that this divergence operator nabla with dot product on this product, which means the electric conductivity times the gradient of the electric scalar potential is operating on it. And as we already have discussed quite often, that in the strong form where we have the partial differential equation, we have a spatial derivative on a material parameter, which is then clearly a problem when you directly solve it, for example, like using the finite difference method. However, as we use the finite element method, we first transform the strong form to the weak form, the variational form, and there we will get rid of this spatial derivative on the material parameter. The standard boundary condition as shown here is that we can prescribe, for example, the electric scalar potential at some value or at zero, a homogeneous Dirichlet boundary condition, or we can define the injection of a current density in normal direction on a surface gamma n, n standing here for the natural boundary, since such a boundary condition here is directly incorporated into the weak formulation. Now have a look also to the heat conduction equation. So we know we have here the time derivative, we have here the scaling of the time derivative with our material parameters, which is the density rho and the specific heat capacity Cm. And then we have the same operator as in the PDE for electric flow, where we have the divergence on the heat flux being expressed by minus the gradient of T scaled here with the heat conductivity K. And on the right hand side, we have here any heat production term in watt per cubic meter, which is in our case already expressed here by the scalar electric potential. So the classical joules losses we have within conductive bodies where a current J is flowing. And here we also can have our standard boundary condition that we prescribe on some boundary gamma E, our temperature. We can prescribe any heat flux on a boundary, and also very importantly, especially for simulating electrical circuits, is that we also have the possibility to take into account a heat transfer on a boundary by our heat transfer coefficient alpha, which is not easy to be obtained. Very often you need a kind of a fluid dynamic simulation to get reliable results, or you do measurements to get a correct heat transfer coefficient alpha. Now, what we can see here concerning especially our material parameters. So we have here the electric conductivity, which depend on the temperature. So this is then a known quantity because we will do an iterative coupling between these two partial differential equations. And we have the thermal conductivity K, and we have the heat capacity Cm, and these two may also depend on the temperature. So the partial differential equation of the heat conduction itself, in this case, would be a nonlinear partial differential equation. And as the direct coupling from the electric flow to the heat conduction, we clearly have the joules losses, which we already have written here on the right hand side of the partial differential equation for heat conduction. Within the exercises, you will do some simulations, but there we will not consider the material parameters to depend on temperature, and therefore it is not as complicated. So it is just a kind of a forward coupling from the electric flow to the heat conduction. Okay, however, if you try to take these parameters into account, which is also important for any coupled simulations, then the most efficient way is as shown here. You have a iterative coupling between these two partial differential equations, which means we have an outer iteration loop with iteration counter k. And as it is standard, we first need some joules losses in order to heat up our structure. We first solve within each time step for the electric flow. Then we get the solution in form of our scalar electric potential, can obtain and compute the joules losses, and therefore when we go over to the heat conduction problem, the right hand side, the heating term for the heat conduction partial differential equation is a known term. We can have here some iterations when we take into account the nonlinearities within the material parameters of the heat conduction, which is the thermal conductivity K and the volumetric heat capacitance Cm, and then you have to solve this within an iterative loop. We call here the iteration counter I, so that's the inner iteration. If you converge, so from one time step to the next time step, it is accurate enough so the temperatures not really change, then we check the outer convergence, the iteration between our heat conduction and the electric flow equation. And here you can see the nonlinearity in the heat conduction is mainly done by a fixed point method. We will not go into detail, however, there is a follow-up lecture in the summer term where we will also deal with nonlinear partial differential equations, but it is like you have a nonlinear algebraic equation. You know, the simplest form is a fixed point iteration, and the more efficient one is a Newton iteration. However, the nonlinearities within the material parameters of the heat conduction are not as difficult, so that mostly the fixed point method is efficient enough. And you see the stopping criterion, we cannot get the accurate, fully accurate solution. So we have to decide how often we do this iteration as shown here. And the standard stopping criterion is that we just look the difference between the temperature we have just obtained to the temperature in the previous iteration and normalize it to the right hand side. Okay, so and a standard value is 10 to the power of -3. So this is a relative norm that would mean we have an accuracy of 0.1%. When we take this as a relative norm where we use in the denominator the right hand side of the heat conduction equation, which are nothing else as our heat sources coming from the electric flow equation. Yeah, and the outer iteration, what we have here, is mainly done by the Joule's losses. So when we again compute here for the electric flow equation, we can compute the Joule's losses within each finite element. We take the difference of these Joule's losses to the previous iterative state. We square it, sum it up for all finite elements, and then take the square root. That's the standard L2 norm. So I should perhaps write it also here. So this is the standard, as we call it, L2 norm. And again here, a standard value is that this should be smaller than 10 to the power of -3. So we also take here a relative norm. Now the normalization is done by the just computed Joule's losses in the L2 norm. So it is fk plus 1, where k is the outer iteration counter. Okay, so this would be the coupling scheme. So you see very often you do not solve the two physical fields together in one big system, but you solve each physical field individually and then iterate between the solutions of the involved partial differential equations. Here I want to give you just a practical example that was a cooperation with Infineon Technology in Villach. So as you know, mainly the death of a semiconductor, especially the power semiconductor, is due to mechanical stresses coming up to strongly varying temperature fields, and the as we just have seen here, these temperature fields are generated by the Joule's losses. And so it is important that you also include with any complex electronic circuit a temperature sensor, which is used as a monitoring sensor concerning the temperature, and then you can decide if you switch off your, for example, power electronic device in order to protect it from too high temperature gradients within your device, and therefore perhaps having a problem with too large mechanical stresses in such a device. The goal here was to do simulations and get the idea how good this temperature sensor is working. And we will see it is a simple resistive temperature sensor. However, the main problem is the sizes of the chip is quite large compared to the sizes of the temperature sensor. So when you fully resolve all details, you end up in a too large computational mesh. And what we applied there was so-called non-conforming grid techniques, which I will just show you on the next slides. So you can see here the layout. What we have here is exactly the layout of just a zoom within our full device here. And in order to have a computational mesh which gives you in a reasonable time a solution, you can use and do not resolve the details of this temperature sensor. So you see here the top of the temperature sensor that is here a resistive temperature sensor with a meander shaped part here, what we can see here. Okay, so in this sense, a possibility is here to do a homogenization. And as you can see on this picture here for the conforming grid, the details were not resolved. On the other hand, we used the following, that we resolved the details, but since in the ambient region we can have quite large element sizes, we used non-conforming grids, which means that immediately at the interface the element size can jump and you have a non-conforming grid. That needs special treatment. Actually, what you need is to fulfill the physical interface conditions on such an interface where the grid size is jumping. However, by this method, we could fully resolve the temperature sensor, and in the ambient region, we could use quite large finite elements to resolve the other details of the power electronic power device. So what we see here is now clearly the following. When you have here this full chip simulation and you look here where we have used our conforming grid model, then clearly we cannot get a physical temperature distribution within the sensor element as shown here, because we have not resolved the geometric details. However, on the other hand, if we look on this picture here, we see that with non-matching or non-conforming, also named grid, we see here a fully resolved temperature distribution within the temperature sensor, which clearly just can't be done since we resolved here with small sized finite elements all the geometric details. What you perhaps also can see here, there is a smooth transition from these small element sizes, finite elements, to the large finite elements, and you do not see here any disturbances. Okay, so this detailed model is just possible with such a special method, so-called non conforming or non-matching grid methods, and therefore you fully can resolve also the details of a very small scale part within your electronic device. Yeah, what we also can see here, this is now a line plot. I should take this on. So as you can see here, put this away. And this is now along this line here, and clearly with the non-matching grid simulation, we get here all the details out, and it is clearly not possible with our conforming grid simulations. You see here a small increase in this part where the sensor is placed. However, it is totally different of it. There is also here the zoom out where you clearly can see we even resolve here the different temperature levels we have within this meander shaped temperature sensor. And what you can see here is also that we get here clearly a better match to measurements when we fully resolve the temperature sensor in such a case. So you see here just due to a switching on of the device, how the temperature increases, and you see that it is also in a very short time it increases. And so with such a approach, it's possible clearly to really do such simulations and optimize the sensor structure in such a sense that we get a reliable sensor for protection of especially power semiconductors.